Okay, welcome back everyone. In this video, we shall explore a more interesting example of differential equations that you might encounter in a controls problem, coupled dynamic systems. So you guys probably know by now what a dynamic system means. A dynamic system is any model, any system that can be modeled by an equation that has a derivative with respect to time. That's a dynamic system. What do you mean by coupled? Alright, what do we mean by coupled? We shall explore that in just a second. I'll show you. You have my word, and I'm a man of my word. The example that I shall be exploring comes from this wonderful textbook by Dr. Smith and Dr. Campbell. It's called a first course, I believe. It's called a first course in DFQ. A first course in DFQ. Now, if you're a engineer and you want to learn differential equations, but you don't want to get boggled in a lot of mathematical details, this book is a 10 out of 10. Very practical. And it has knowledge that you can actually use. So go check it out. First course in differential equations by Scott Campbell and Carlos A. Smith. All right. Now we shall move on to the main problem itself. Okay, so we have the problem itself. Our first differential equation, derivative with respect to time, plus x of t is equal to 3y. All right, x and y are variables that vary with time. This shall be my first differential equation. The next equation is going to be y of t minus the derivative with respect to time, dy dt. Y of t is equal to 2 times x of t, and this shall be my second differential equation. If you've taken a numerical methods class and you've played around with Euler's method or Runge-Kutta, etc., you guys might have an idea. The first step in using those numerical methods is to rewrite these equations in this form so that you have your derivative terms on the right side, the derivative terms on the right side, on the left side, sorry, I'm a little dyslexic today, please apologize. And okay, everything else on the right hand side. So we're gonna get x of t plus 3y of t for the first differential equation, and for the second differential equation we're gonna get 2x of t plus y of t. Please check my algebra. I am quite confident in my algebra on most days, but I can make a mistake. So, well, no, this is good. This is correct. Never mind. So we have the derivatives on the left-hand side, all my dy dt terms on the left-hand side, and I have the rest on the right-hand side. Left-hand side. Let's just make it more explicit so that you guys don't get a little intimidated. Nothing fancy here. Now, where does the term couple come from? Now, let's explore that. Couple. A couple of flowers, a couple on Valentine's Day. What do we mean here? What? You see, now let's take the first differential equation. Let me highlight it for you. And you'll probably see that the derivative term depends on both x, the first variable, and y, the second variable. It depends on both x and y, so the derivatives are coupled. Hence, dependence on both variables, dependence of derivatives of the x prime, the x dot or y dot. Y dot means the dot represents derivative terms. Dependence of x dot and y dot on both variables. That's the definition of a coupled system. So next time you see somebody throwing these big terms in your face, coupled differential equation, this is exactly what this means. Nothing fancy, all right? Nothing fancy at all. All right. Now, okay, just to make everything more explicit, x dot means x prime of t, y dot means y prime of t, and both mean the same thing as this. All right? Nothing to be intimidated about. All right, nothing fancy here. So just to make everything clear and on the sheet. So we have our now we need to find a solution strategy. Okay, we have our model, but our model is no good if we cannot figure out how to solve this, right? In order to, like I mentioned previously, there are going to be two main approaches. One shall be analytical, and the other shall be, some of you have already guessed it, numerical. All right. Numerical versus analytical. In the analytical domain, you'll have all the professors with OCD who are going to be using linear algebra, and they'll be using disgusting things like eigenvalues and eigenvectors. They're going to be doing all that nasty voodoo magic. I mean, to us engineers, that's voodoo magic. We engineers, this is the and this can give you some really good result, but is it really worth the effort when you're in a practical situation, when you're at work, when you can just approximate? Numerical modeling. Engineers are notorious for approximating stuff. The memes like G equals 10, the memes like E equals pi, where do these come from? They just stem from the fact that engineers approximate a lot. All right, and if you've ever had a actual engineering job, you would know that. An internship or something, you would know that. All right, so that's where the memes come from, and we shall use the memes as our guiding lantern, and they shall show us the way. In the approximate domain, we're gonna use ODE solvers mostly. Yeah, that's what we're gonna use. We're gonna use a bunch of Euler. Actually, that actually comes in the domain of ODE solvers, but we can use MATLAB. The platforms that we can use MATLAB, we can use Simulink, we can even use Excel, and we can even use Python. All of these. I'll try to cover an example in Simulink, in one example in Excel, and one in Python, and maybe one in MATLAB, maybe. So in the next part of this video, we're gonna make a Simulink diagram. For our system. Let me just grab my system from above. There it is. I can just use the power of technology. All right. Shout out to Dr. Fawcett for training me in this. Right, Dr. Fawcett, you're what's known as the real G. Here we go. Bravo. All right. We're gonna develop a Simulink diagram. First, we're gonna sketch it. All right. Since this is not easy, first we're gonna sketch it on paper or like on a tablet, and then we're gonna go in the Simulink interface. That's usually a good strategy. I can spell today. I can spell. Simulink interface, UI, Simulink UI. None of that boomer terminology, okay? Wonderful. So yeah, thanks for watching, guys. We're gonna continue this example in the next video. We're gonna sketch. We shall draw a sketch of the block diagram, and then we'll implement that block diagram into the Simulink UI. And yeah, we explored a couple differential equations, couple dynamic systems, differential equations that have where the derivatives depend on both variables, the x's and the y's. The derivatives depend on both variables. All right, we briefly discussed the solution strategies, and this is going to be our gateway into the next video. All right, thank you so much for watching, and I love you guys. Thank you so much.